everyone. In this video, we'll do some question practice and we'll find out the hybridization of different complexes. So these are some complexes, and I want you guys. I asked in the previous video to you to solve these. I hope you guys have solved. So for the sake of simplicity, I'll be writing the electronic configuration over here up at the top. Manganese, uh, starting with the scandium, titanium, vanadium. I should have written the other way around. So that will be easy for you to understand the 3D and the 4D metals. So, copper, zinc. So I'll ask you guys to remember these D block element series 3D, 4D, and 5D. So for the this one, the electronic configuration is ND1. Okay. The electronic configuration is D1, S2, D2, S2, D3, S2, D4, S2, D, or you can say D5, S1, D5, S1, D5, S2, D5, S6, D5, S7, D5, S8, sorry, D what I did wrong. Okay, D5S2, D6S2, D7S2, D8S2, D10S1, D10S2. Okay, so these are the electronic configuration. Starting with the silver ammonia complex. Okay, with this complex, silver, where is silver? Silver is in under copper. Okay, over here. The electronic configuration is for silver, the electronic configuration is D10S1. Find out the oxidation state over here. X plus 2 into charge on ammonia 0 equal to plus 1. So oxidation state is plus 1. Silver has this electronic configuration. Silver with one positive charge will have a configuration of D10. So fill the orbital. The orbital configuration is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4D is completely filled, 5S is empty, and 5P is empty. Since there are four ammonia molecules, sorry, two ammonia. Over here, two ammonia molecules are there. So, two such ammonia, the hybridization will be S and P. sp hybridization will be there, and two ammonia will be donating their electrons, one each to this two sp hybridized orbitals, and the shape will be linear. Is there any unpaired electron present over here? No. So the complex is diamagnetic as well. Okay, now we'll solve another example. Let me just erase this, erase what we did over here. For mercury, see the electronic configuration in which 3D in which D series the mercury comes. The mercury comes in 6D, sorry 5D series. So 3D, 4D, 5D. The mercury comes in 5D series. The electronic configuration of mercury is, our complex is mercury triiodide minus. Okay, so electronic oxidation state of mercury is X plus 3 iodide minus, has a minus 1 charge. So minus 1 X minus 3 is equal to minus 1 X is equal to minus 1 plus 3 X is equal to plus 2. Mercury is in plus 2 oxidation state over here. Electronic configuration of mercury, you can see over here, is D10S2. Okay, 5D10, 6S2. So mercury 2 positive will have an electronic configuration of D10 only. Mercury 2 positive. Fill the electronic configuration. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 5D is completely filled. We are left with 6S and 6P. How many ligands do we have? We have 3 iodide minus ions. So 3 ligands are there. We will be hybridizing 3 such orbitals, forming a hybridization of sp2. Okay, so sp2 hybridization will be there, and the ligand, each iodide ligand, I minus ligand, will be donating its electrons each to these 3 hybridized orbitals, and will be having sp2 hybridization. Sp2 hybridization has which geometry? Trigonal planar. Is there any unpaired electron? No, no unpaired electrons. So what will be the magnetic moment? Magnetic moment will be 0. We'll be having 0 magnetic moment over here. Okay, it is a diamagnetic complex. But see the electronic configuration for the next metal. We have cobalt tetrachloride, 2 minus. Coordination with that coordination state with 2 minus charge. Find out the oxidation state. What will be the oxidation state for that? So for the next complex, let's say cobalt Cl4, okay, 2 minus. X plus 4 minus 1 equal to minus 2. X minus 4 is equal to minus 2. Oxidation state is plus 2. Cobalt has an electronic configuration of 3d7 4s2. Cobalt plus 2 has an electronic configuration of 3d7. Fill these electrons. 1, 2, 3, 4, 5, 6, and 7. How many ligands are there? We have 3 ligands. We have 4 ligands, 4 Cl minus. And all these are weak field ligands. So weak field ligands cause any pairing? No pairing. So for 4 chloride ion, these 4 orbitals will be hybridized, and they will hybridize to generate a hybridization of sp3, so that 4 chloride minus ions will donate their electrons in these hybridized orbitals, and will be having a geometry. What will be the geometry in this case? For sp3 hybridization, we have a geometry of, what is the geometry for sp3 hybridization? It is tetrahedral. Now you guys tell me, do we have unpaired electron in this complex? Can you see some unpaired electrons? Yes, we can. Where are those unpaired electrons? Unpaired electrons are basically, let me change the color of the pen. Okay. In this 3D orbital, these three unpaired electrons are present. So it is a paramagnetic species with a magnetic moment of, what is the will be the magnetic moment? We saw now in the previous video magnetic moment is equal to under root n into n plus 2. So you will calculate magnetic moment over here with this formula, 3 into 3 plus 2. Okay, calculate the value. Moving to the next example, that is, I think I should have cleared the whole screen. Clear whole screen. Okay. We'll be moving to the next example, that is nickel cyanide. Nickel tetracyanide complex with 2 minus negative charge. What is the oxidation state? X minus 4 is equal to minus 2. X is equal to minus 2 plus 4. X is equal to plus 2. Nickel has an electronic configuration 3d8 4s2. Nickel 2 plus will be having an electronic configuration 3d8. Fill this electronic configuration. 1, 2, 3, 4, 5, 6, 7 and 8. 3d8. S and P are vacant. 4s and 4p are. So we have 4 cyanide ligands. Cyanide is a strong field. Strong field ligand will cause pairing. So what we'll do, we'll pair this electron over here and there will be one vacant orbital generated in the D. So 1, 2, 3, 4, 5, 6, 7, 8. One vacant orbital is generated over here. And we have empty 4s and empty 4p. 3D, we have this configuration. So 4 cyanide ions will come and donate their electrons. So the hybridization could be, we need 4 empty orbitals. So this could be the hybridization D2 DsP2, sorry, DsP2. One d orbital is there, DsP2. In case of tetra coordinated complexes, where the inner d orbital is involved, the hybridization is DsP2. In that case, the geometry is square planar. Geometry is square planar. So can you see some free electrons? No. So the complex is diamagnetic. Diamagnetic, but will be the magnetic moment. Magnetic moment is equal to under root n into n plus 2. Since n is equal to 0, number of unpaired electrons are not there. So magnetic moment will be equal to 0 into 0 plus 2. That will come out to be 0. Magnetic moment is equal to 0. Okay. We move to next example. That is permanganate. Alright. Kf Mn4 minus. We have a potassium permanganate. So this is permanganate. Permanganate. Find the oxidation state. X plus 4 into oxygen has a charge minus 2. Overall minus 1 charge. X minus 8 is equal to minus 1. X is equal to minus 1 plus 8. X is equal to plus 7. What is the oxidation state of manganese? Manganese and electron configuration 3d5 4s2. If manganese has a charge of plus 7, that means 5 and 2. 3d is vacant. All 7 electrons are lost. So we have for manganese 7, we have an empty 3d, empty 4s and empty 4p. No electron is present in 3d, 4s and 4p. How many ligands are coming? This oxygen O2 minus oxide ion is coming. So how many of them are coming? 4 of them are coming. So since 4 of them are coming, we'll be needing the hybridization. Hybridization will be including the empty d orbitals. So in this case, the hybridization will be sd3. sd3. In these hybrid orbitals, 4 O2 minus ligands will donate their electrons and form a covalent coordinate bond. For this sd3 hybridization, geometry will be, what will be the geometry? Geometry is tetrahedral. Are there any unpaired electrons? The electrons that will be coming over here will be like this. So since there are no unpaired electrons, the complex is diamagnetic. And the magnetic moment will be mu is equal to n into n plus 2. Since n is equal to 0, magnetic moment will come out to be 0. Similarly, you can see for the case of chromate ion, perchromate. Okay, for the case of CrO4 2 minus, oxidation state will be X plus 4 minus 2 is equal to minus 2. X minus 8 is equal to minus 2. X is equal to minus 2 plus 8. X is equal to plus 6. Chromium has an electronic configuration of 3d 5 4s1. Chromium plus 6 has an electronic configuration. All the 6 electrons will be removed. 3d 0, 4s 0. So we have an empty D3D, empty 4s, and empty 4p. Similar to the case of permanganate ion, so 4 oxide ions are coming. So what will be the hybridization? Hybridization will again include s and 3 inner d orbitals. So the hybridization will be d3, and each of the oxide ion will be giving the electrons to this hybrid molecule, and the overall geometry is tetrahedral shape, and the magnetic moment is 0, since mu is equal to under root n into n plus 2. N is equal to 0 over here. Coming to the second another example, that is iron pentacarbonyl complex. Find out the oxidation state. X, let's suppose X is the charge on iron, plus 5, carbonyl is a neutral ligand. Overall charge on the complex 0, neutral complex 5. X is equal to 0 is equal to 0. Iron is neutral. There is no charge on iron. Iron has an electronic configuration 3d6 4s2. Okay, you will fill the electronic configuration over here. So 1, 2, 3, 4, 5, 6. 3d has 6 electrons. 4s has 2 electrons. 4p is empty. So since 5 carbonyls are there, and carbonyl is a strong field ligand. So what will happen? Pairing will happen. These molecule will come over here, and this molecule will come over here. We'll be having one vacant D. S will be, so if we do the overall pairing, iron has 3d6 4s2. So actually the complex over here, mentioned over here, has a plus charge of, has a has 2 plus charge basically. Sorry, I did a mistake over here. So it has a 2 plus charge. So iron 2 plus will be, these 2 electrons won't be there. I did this mistake in copying the question. This is iron 2 plus. Okay. So these electrons will be paired up, and what will be we having? No. It is okay. It is actually, sorry, my mistake. It is that only. So if I pair up the electrons 1, 2, 3, 4, 5, 6, these electron I pair up, I'll be having 2 electrons on the F. since we need five orbitals, so these two electrons will be again shifted to the inner d orbital. So the hybridization will be like this: 1, 2, 3, 4, 5, 6, 7, 8, or 8 electrons are filled inside the d orbital, and we have a vacant d, we have a vacant s, when we have 3 vacant p. So the hybridization for 5 coordination will be dsp3. Okay, dsp3 will be the hybridization, and each cardinal will be donating its electron over there. And for dsp3 hybridization, what will be the geometry? The geometry will be trigonal bipyramidal. Trigonal bipyramidal. That will be like this: a trigonal plane, and one above the trigonal plane and one below the trigonal plane. Okay, we'll come to the next example, that is nickel cyanide 5 3 minus. Oxidation state: x plus 5 into minus 1 is equal to minus 3, x minus 5 is equal to minus 3, x is equal to plus 2. Nickel has an electronic configuration 3d8 4s2. Nickel plus 5 plus 2 has an electronic configuration of 3d8. Fill the electronic configuration: 1 2 3 4 5 6 7 8. Okay, now this is 8. Okay, s is vacant, 4s 4p, 3d8. We have 5 cyanide ions. 5 cyanide strong will cause pairing of electrons. The electron present in the d will be paired, and one empty d orbital, inner d orbital, will be generated. So 1 2 3 4 5 6 7 8. This is empty now. This is 4s and this is 4p. 4s and 4p. Okay. For 5 cyanide, we need 5 hybrid orbitals. 5 hybrid orbitals will include dsp3. Again, the hybridization will be dsp3, and for dsp3 hybridization, geometry is trigonal bipyramidal. Okay, we'll come to the next example, that is iron cyanide 6 and F6. Iron CN6 4 minus, x minus 6 is equal to minus 4, x is equal to plus 2. Iron is in plus 2 oxidation state. Iron plus 2 oxidation state. Iron has an electronic configuration 3d6 4s2. Iron plus 2 will have an electronic configuration of d6, filling those 6 electrons in the 3d: 1 2 3 4 5 6. So since 6 cyanide ligands are present, so these are strong ligands. That strong ligands will cause the pairing of electrons. So we'll be having an electronic configuration like 3d 4s 4p. Pairing will occur, therefore we'll be having electronic configuration like this. Since we have 6 cyanide molecule, we need 6 hybrid orbitals. 6 hybrid orbitals will include 2d 1s and p. 1 2 3 4 5 6, sorry, will be involving this one as well. So we'll be having this as well. We need 6 hybrid orbitals. D2sp3 will be the hybridization, and the 6 cyanide ligands will be donating their electron in these 6 hybrid orbitals, and therefore we'll be having an inner orbital complex with D2sp3 Hybridization and the shape of the geometry will be octahedral. Magnetic moment will be 0 since there are no unpaired electrons present. Coming to the last example, that is iron Fe6 3 minus. Oxidation state will be x6 into fluoride has minus 1 charge minus 6, x minus 6 is equal to minus 3, x is equal to minus 3 plus 6, x is equal to plus 3. So iron has an electronic configuration of 3d6 4s2. Iron plus 3 will be having an electronic configuration 3d5. Since fluoride is a weak field ligand, 1, 2, 3, 4, 5. Okay, iron 3d5 we have electronic configuration, 4s is empty and 4p is empty. So since it is a weak field ligand, therefore it won't be causing the pairing of electrons. Therefore, when six fluoride ions will come, they will rather, the complex will rather do the hybridization in this manner where it will include sp3d2. Outer D will be included, 4d will be included, and in that case, we'll be having sp3d2 hybridization having a shape of octahedral geometry. We'll be having octahedral geometry. Number of unpaired electrons over here 1, 2, 3, 4, 5. 5 unpaired electrons. So there will be some magnetic moment. That is n into n plus 2. That is 5 into 5 plus 2. So calculate this value. You will calculate the magnetic moment. The species is a paramagnetic species. So these are the geometries and their hybridization and their coordination number. And this is some other example where you can see that generally sp3 has a tetrahedral geometry, dsp2 has a square planar, sp3d has a triangular bipyramidal, sp3d2 and d orbitals are used, that is outer d orbitals are used over here. It forms an outer orbital complex or high spin or spin free complex, whereas if inner dsp3 hybridization is there, then there is formation of inner orbital complex. It is formed generally by pairing of electrons. Both d2sp3 and sp3d2 has geometry of octahedral. So there are further some questions for you guys to understand and to solve. So tell me, is iron hexafluoro ion, this 3 minus ion, is it an outer orbital complex? Solve it and then tell me. So basically calculate the oxidation state first. X minus plus 6 into minus 1 is equal to minus 3. X minus 6 is equal to minus 3. X is equal to minus 3 plus 6. X is equal to plus 3. Iron has an electronic configuration 3d6 4s2. Iron 3 plus will be having an electronic configuration 3d5. So fill up those 5 electrons in the 3d orbital 1, 2, 3, 4 and 5. 3d5. 4s is empty, 4p is empty. So we have 6 F minus ligand. Are these strong or weak? As we know that halogens are weak field ligands. So will they cause any pairing? No pairing of electron will be there. Since there is no pairing of electron, that means we need 6 orbitals, hybrid orbitals, including outer D. Hybrid orbitals including outer D orbital. How will that be possible? 3D inside only. Let it be. It won't be used because all the orbitals are singly filled and we can't put electrons in them. So therefore we'll use outer 4D orbital. This is 3D, this is 4S, this is 4P, this is 4D. Okay. So 6 orbitals are required. 6 hybrid orbitals. sp3d2. Okay. So The question is sp3d2 will be the hybridization. The question is this is an outer orbital complex? The answer will be yes, because we are using outer D to generate the hybridization we calculated to be sp3d2. That's why it is an outer sphere complex, outer orbital complex. Okay, so outer orbital complex as it shows an hybridization of sp3d2. Coming to the next question, calculate the hybridization of nickel chloride 2 minus. Nickel chloride tetrachloride 2 minus x plus 4 minus 1 is equal to minus 2 x minus 4 is equal to minus 2 x is equal to plus 2. Nickel has an electronic configuration 3d8 4s2. Nickel 2 plus will be having an electronic configuration 3d8. Fill up that electrons in the orbital 1 2 3 4 5 6 7 8. 3d8 we have 4s empty, we have 4p empty. Chloride is a weak field ligand. Again, no pairing of electrons. So hybridization will be include outer d orbitals. We have 1, 2, 3, 4, 5, 6, 7, and 8 electrons over here. This is S, this is P, and we have outer 4d orbital. Okay, S, P, 4d, 4s, 4, for 6 electron 6 for 4 sorry. Okay, so for 4 electrons, 4 ligands, we will be needing 4 hybrid orbitals. Those 4 hybrid orbitals will be used as sp3, and therefore the hybridization will be sp3. This is our hybridization sp3, and the geometry will be tetrahedral. Okay, third question, is nickel chloride a paramagnetic species or diamagnetic species? As you have done in the previous case only, the it is actually nickel chloride 2 minus. So nickel has an electronic nickel has a oxidation state of plus 2. It is the same example that we did in previous slide. So as you can see here, we have 2 unpaired electrons. Because we have 2 unpaired electrons, that means the species has some magnetic moment. So magnetic moment we can calculate by mu is equal to under root n into n plus 2. That means n number of unpaired electrons we saw it equal to 2. So magnetic moment is equal to 2 into 2 plus 2. It will give some value under root 2 into 4. So it is 2 root 2 something. Okay. There are 2 unpaired electrons in the present in the nickel chloride, so the complex is paramagnetic in nature, as I said. Okay. So we'll discuss crystal field theory in the next class. Thank you for watching. Bye bye.